All right, greetings everyone. Welcome to the first part of the video for section 4.3, moving right along in chapter 4. First thing I want to say is this GIF here, it is one of my favorites of all time. However, it does give me a headache after I start to see it replay for like the 10th time. So should I sit on this for a little bit so we're forced to watch it more times? No, let's move on. Come on, we got stuff to learn. Okay, so we've been talking about exponential equations or exponential functions at the beginning of chapter 4. And now we're going to look at solving exponential equations. So here's an example. So how could we solve the equation 2 to the x equals 12? Let's first try to do some brainstorming on this based on stuff we know so far. Well, one of your instincts might be to try to divide both sides by 2. However, what's the problem with that? Well, we can't really just cancel out these 2's on the left here because there's the x in the exponent, right? So that will not work. So we can't divide by 2. Similarly, if we try to subtract 2, right, on both sides, that's not going to work either, again, because this 2 here is being raised to an exponent. So it looks like using the methods we know at this point, we cannot solve this equation. So we're going to need a new tool. Let's also think for a minute if we could estimate a range of the values for x up here, just for kicks and giggles. So what values must x be between? Well, when I look at this, I know that 2 to the third equals 8, and 2 to the fourth equals 16. And notice that 12 is in between 8 and 16, which tells us that x is going to have to be between 3 and 4. Okay, so whatever the actual answer is for x, it'll be somewhere between 3 and 4. Also notice that 12 is right in the middle between 8 and 16, so it's 4 units away from 8, 4 units away from 16. So it tells us x is probably going to be somewhere around 3.5. But again, since we're mathematicians, we want to try to find an exact answer. And as I mentioned, we'll need a new tool. So what is that new tool? So that would be logarithms, okay? So logarithms are basically another way to write exponential equations. And one way I usually think about logarithms is that they represent exponents, okay? So we're given here in this definition here, the statement b to the a equals c is equivalent to log base b of c equals a, and that's how that's said. Log base b of c equals a. So what is this saying? Well, let's add some numbers in here. So let's say in exponential form, we have something like 3 squared equals 9. Okay, so that, in this case, the value for b would be 3, the value for a would be 2, and the value for c would be 9. Well, let's rewrite that in this log form now. So in log form, what we would have is log base b, which in this case is 3, of the value for c, which is 9, equals 2. And hopefully you see from that then what I said before is true, right? That the logarithms are really representing exponents. So if we see log base 3 of 9, what we're asking is what power does 3 have to be raised to give the value 9? And the answer is 2, right? So with that in mind, let's look at some other examples of logarithms. So let's say we had something like log base 10 of 100. Well, what's that going to be equal to? Well, that's also going to be 2, right? Because again, what this is asking over here is 10 raised to what power will give us 100, and the answer is 2. All right. What about log base 4 of 64. Well, again, we're asking what power does 4 have to be raised to give us 64? In this case, the answer is 3. Okay, because 4 to the third would give us 64. So that's how logarithms work. Now, the reason these are helpful, okay, so if we have, going back to that example we were just looking at, 2 to the x equals 12, well, if we write that in log form, the way we can do that is log base 2 of 12 equals x. And even though we're still stuck with the problem here of finding, to what power 2 has to be raised to give 12, notice at the very least we've been able to write an expression that doesn't contain any x's on one side of the equation, and in fact we've been able to isolate the x. Okay, and we'll get more into how to figure these things out here in a video or two. All right, now because there's that relationship between logarithmic forms and exponential forms, it turns out that logarithms and exponentials are inverse functions of each other. And this is important because this allows us then to solve equations. So as an example that's not logarithms, recall that if we're going to solve something like x squared equals 9, well, we solve this by doing the inverse operation on the left-hand side. So the inverse of squaring something is square rooting it. So we do that on the left and the right, which will give us x equals, and we know with roots we'd have plus or minus, so plus or minus 3. Okay, so again, we use an inverse operation there. We do a similar thing if we have, say, square root of x equals 6. Well, to solve for x here, we again use inverse operations, and the inverse of square rooting something is squaring something, so we do that on both sides and end up with x equals 36. Okay. Well, logs and exponentials have a similar property. So for example, let's say we were going to solve something like 3 to the x equals 17. Okay. And we need to isolate, actually, let's not do 17. Let's do 27. Okay, and we need to isolate that x over there. Well, based on what we see over here, logs and exponentials are inverses of one another. So what we can do is on the left-hand side here, do a log base 3 of 3, and do the same thing on the right-hand side. And what that'll do on the left-hand side is effectively undo the log and the 3 and just leave us with x. And on the right-hand side, we'd have log base 3 of 27, which we know would be 3 because 3 to the third equals 27. All right. We do a similar thing if, let's say, we were trying to solve something like log base 2 of x equals 4. Well, notice, and this one's sometimes a little bit harder to see, again, it says that b, so log base b of x equals x. So basically, again, exponentials and logs are inverse of each other. So what we can do here on the left-hand side is make this 2 to the log base 2 of x. Do the same thing on the right-hand side, make this 2 to the fourth. Again, the 2 raised to the power and the log base 2 cancel out. We're just left with x equals 2 to the fourth, which equals 16. Okay. So again, what I want you to get from this is that logs and exponentials are inverses of each other, and so that allows us to use them interchangeably when solving equations. All right, so let's just do some practice here, rewriting exponential stuff in log forms and vice versa. So here 4 cubed equals 64. We're going to write that in log form. It's going to be log, and then the base of the exponential, so that's the 4, that becomes the base of the log, so a log base 4 of, and the number on the other side, 64, that becomes the thing that's inside of our log, which then equals 3, the exponent. And again, we just saw an example like this, right? Log base 4 is 64 means to what power does 4 have to be raised to give 64? And the answer is 3. Okay. All right, on the next one, 5 to the p equals q. So here, we don't have any numbers except for the 5, but we can still do this, right? So it'd be log, again, our base here is 5. The number we get is q equals p. And again, the question over here on the left is 5 to what power gives us q? So log base 5 of q is saying 5 to what power gives us q? And the answer is p. Right? All right, let's also go the opposite direction. So log base 3 of 27 equals 3. Well, now we're going to write this in exponential form. So the base of the log becomes the base of the exponential. The 3 over here, that's the exponent. And then that equals 27. Okay. And then finally, this log base 4 of n equals k. Here we would do 4 as the base raised to the exponent, which in this case is k, equals n. So that would be our expression there. 4 to the k equals n is the same as log base 4 of n equals k. All right, so now you can imagine that for some of these instances, right, you're not going to be able to know off the top of your head or even by hand what the exponent is. For example, if I ask you to find what log base 4 of 5 is, well, that's saying to what power do I have to raise 4 to get 5? Well, I don't know about you, but I don't know that off the top of my head. So we have to use our calculators somehow. So let me go to our calculator. Here we go. And there is on some calculators an additional log function to the one I'm going to show, but what I want you guys to focus on are these two buttons right here. Okay, next to the 7 and the 4. So we have just a log, one that just says log, and then a button that says ln. And log, okay, when you see a log without a base written, what that is actually saying is log base 10. So in our calculators, if we were to do, say, log of, say, 1,000. Well, again, this is saying log base 10 of 1,000. So we're asking to what power do we have to raise 10 to get 1,000? We know the answer is 3, and note the calculator gives us that. But what the calculator can also do for us is find log of numbers that are not powers of 10. So for example, let's say we want to know log of 199. Well, I don't know about you guys, but off the top of my head, I can't tell you to what power 10 has to be raised to give me 199. So go ahead and press enter there. And notice that it gives us the answer as a decimal, so 2.298853076. Okay. Now, natural, or ln, this one is read as natural log. And what that's really equivalent to is a log where the base is the number e. So remember, e is Euler's number, the number that's about 2.718 stuff. Okay. And we can see that by, if we plug in the calculator, ln of e, do e to the first, which, recall what this is saying now is log base e, because ln means log base e of e, says to what power do we have to raise e to get e? Well, the answer there should be 1, right? Because anything to the first power is itself. And we can, again, see that we get that here. Similarly, if I did say something like ln of 5, well, I don't know what power e has to be raised to give me 5. The calculator can figure it out for me. Okay? All right, that's it for now. Thank you for watching.